Okay, hi guys. Okay, we will leave the introductions for next week. So the two new members will introduce themselves next week. I think we have a lot to cover today, so let's get to it.
Okay, hi everyone. I hope you all had fun in the first session. So today we'll be doing part 2 of the multi-layered perceptron. So I'll do some recap first, then maybe I answer some queries that some of you all have asked me last week. Then we go into what we want to do today, which is using this multi-layered perceptron to classify some images. So yeah, hope it'll be fun for you. So as always, let me just begin with some of the ground rules I have. So basically, I like to encourage question asking, like to encourage more of like understanding the concepts more than the math. So my slides have very little math. The math will be referred to in some links. Okay, I'll actually point out where the detailed math should be if you actually want to follow up on it. Okay, so this will be a recap of like what we covered through last week. So last week, remember there was this thing called the gradient descent. So gradient descent is as follows. Okay, if you were suppose that you are an explorer somewhere in the valleys or mountains, and you want to like maybe find the lowest points. Okay, but you only have understanding of where your local surrounding is. Okay, so you may not be able to like have a god eye view of where everything is. So the best bet or one of the easiest ways to try to find the lowest point is just to look around you and just find where's the minimum point from that position. So if we were to look at this plot, okay, we will just go to the slope where the gradient is the highest for each point. So we keep doing this, and then sooner or later, okay, we will hit some minima. Okay, and in this case, the minima is all the way down here. So this idea of like doing gradient-wise, stepwise gradient update is called gradient descent, and it has proven quite useful in many deep learning models, trying to find where the loss function is at its minimum. Okay, so if you recall from last week, the loss function is very crucial in terms of our deep learning system, because by minimizing the loss, we are trying to tell the model, okay, I want you to model this function. I want you to fit like in the sense of like what we did last week, like the set of 1, 2, 2, 3, 3, 4, 4, 5. We want to fit the x that can a function that can map x to your y values. Okay, and then this loss function will try to ensure that the function goes there. So essentially, that is more or less the theory of gradient descent and like neural networks in general. So this graph is the graph again from last week, where you have a minimum point here, where you have a parameter like a weight, you want to minimize it. So you just step through at each point, you calculate the gradient with respect to your loss function. You step through and move towards the minimum point. And the equation is given here. The weight update equals to the original weight minus your learning rate times your gradient. Okay. So this is a backprop. So backprop is basically at first you step forward. Okay, you go forward in terms of your input is your blue color. You go to the next node, and then you compute the forward one for your next node. Before you do backpropagation, where you backpropagate the errors backwards from the outputs, the loss function, you backpropagate to your middle node to your input nodes, and this can be expanded for even larger graphs. Okay, this is just a simple illustration. Okay, so now that was the recap. Yeah, just any questions for those who would like to ask before I move on to today's topic? Okay, so the first part that I would like to do is to expand the kinds of gradient descent that we have touched on. So last week, remember we touched on this stochastic gradient descent. There are actually many more versions of gradient descent that can actually help us to get the better convergence. Okay, so let's take a look. Okay, before we go into that, just going to illustrate this thing here because this will be useful for today. So there's this thing called the batch size when we do training. So batch size is basically like when you pass something through the network. Okay, let's say you have 6 images. You can either pass all 6 at one go, which in this case, if you do that, your batch size will be 6. Okay, so but in practical cases, you may not have the capability to store all this, like let's say 6 is 6 images. You may not have the capability to store like all these 6 images worth all into your RAM, rapid access memory for your computer. So you might need to split them up into smaller batches in order to do training. So the batch size refers to like the number of samples that you have. So normally like images, or it can be text files. So the number of samples that you pass into one run for your forward pass of your network is called a batch size. Okay, then basically what we have next is we have this thing called the epoch. So epoch will basically mean how many times have we iterated through the entire data set. So you can see like over here, the first part here is epoch is 1, because although we split into 2 batch size of 3, we only look through the entire 6 images once. So epoch is once. Same for B also, you split in the batch size of 2, so you get 3 sets of 2, but your epoch is still 1. The last one, okay, we iterate over 12 images, 6 and 6. So we iterate over the data set twice. So that means we iterate over 2 epochs. Okay, so these terms will be very useful later, because in TensorFlow, they also use the terms batch size and epoch. So this will be quite crucial to understand what's going on when we train our network. Okay, then there's another last term here called the iteration. In this case, iteration just refers to the number of times you pass data through your network. So like, for example, if I pass 3 images to the network gives me like some form of output. Okay, every pass I make to the network is 1 iteration. So you can count like there are 2 iterations for the first one, 3 iterations for the second one, 6 for the last one. Okay, so these are the simple terms. The main thing to take note of is batch size and epoch, because these will be used in practical deep learning. Yeah, pause here if you all have any clarifications on this. Okay, because next up, we're going to do an advancement of gradient descent using this batch. Okay, so, all right, so let me just tell you all what this is. Okay, so in terms of normal gradient descent, okay, in normal gradient descent is something like this. Every time we go through a sample, we pass through the network. The network updates the gradients using the equation that we seen earlier. So the equation is, the equation is this. Let me just do my annotation. The equation is this, like W equals to W minus, you all still remember what is this? Minus the learning rate times, okay, times DL, your loss with respect to your parameter. So this is like my stochastic gradient descent. I basically, for each time I pass through a sample, I find the gradient and then update my weights accordingly, or update my parameters accordingly. So you can be sure that when you do this, you may not be able to get the right update straight away. Okay, it might actually look through like up and down very messily, because some samples can be noisy. So you update it very noisily, but overall the general trend, your loss should go down. Okay, but it will be a very bouncy way of doing the loss function. Okay, so what people have found is that if we were to delay the weight update, okay, instead of just updating it over every sample, okay, what if I update it over the entire batch? Okay, so this is the idea of batch gradient descent. So like for every batch, okay, I update my loss function like that. So like batch 0 to batch 1. So I run through my entire training data. Okay, and then after that, I accumulate the gradient updates. Then I update all at one go. Are you able to see my text, by the way? Yeah, so basically, what this means is that, for example, over here, okay, we change our weights every sample. So every time you pass an image through the network, your weights change accordingly. So the next time you run through the network, they will use updated weights. Over here, what it does is that it goes through the network, it gets all the gradient updates. So maybe like weight plus 0.1, weight plus weight minus 0.2, weight plus 0.3.
Could you darken the color of your, because it's very light. So
okay, how's this?
Yeah, this is better.
Okay, thanks for pointing it out. So let's say in sample 1, we have this weight, sample 2, we have another weight. Okay, so this is the adjusted parameters for your weight. Okay, so normally for stochastic gradient descent, I'll update my weights the moment I get it. Okay, so what we do is we accumulate, and then what we will get is plus 0.1 minus 0.2 plus 0.3, that will be plus 0.2. Okay, so batch gradient descent runs through the entire batch. Okay, update all the weight updates, accumulate all of them, and then we update at one go at the end of the batch. Okay, so as you can see, it kind of averages out all the different directions your gradient can go into. And it is, in general, it is a smoother update. Okay, but the reason, okay, there's one, I mean, if batch gradient descent was so great, okay, everyone would be using batch gradient descent. So can you think of one reason why, batch gradient descent may not be as feasible as maybe stochastic gradient descent? Anyone want to like do a guess? Like, why don't we use batch gradient descent as the default for like training deep learning models? So you just go through the entire batch, then you update the gradients one time. Anyone want to guess? Okay, so I give you some options. Okay, so it is either, okay, the gradient update is too small, or the gradient updates take too long to converge. Anyone want to guess? Like, why don't we do batch gradient descent? Okay, so maybe I'll just share, okay, because in the interest of time, the reason why batch gradient descent is not so preferred is because looping through a batch takes very long. And by the time you loop through the entire batch and you update your parameters, okay, stochastic gradient descent might already learn, like, for example, in one epoch, okay, okay, if we have one epoch, oh, wrong color, hang on. So in one epoch, maybe this is one epoch worth. Your stochastic gradient descent already reached this point. But in one epoch, your batch gradient descent only reaches this point. So you can see that you require a lot more times to pass through the parameter, pass through your entire training batch in order to update for batch gradient descent. But in general, it's a smoother curve. Okay, it's a smoother curve, it's a nicer curve. So what people have come up with, okay, one is nice, one is great for like converging because it's a very smooth update. One is noisy, but one is faster to converge. One is a little slower. So people find the in-between. So the in-between is called, no surprise, it's called mini-batch gradient descent. So mini-batch gradient descent is a very simple thing. So instead of like going through the entire batch, I go through like X number of samples. Like, for example, I go through X number of samples. Okay, based on batch size. Okay, accumulate, gradient, and update. Okay, so it's a in between. So stochastic gradient descent updates my parameters once per sample. Batch gradient descent waits until the entire batch is done, then we update. But mini batch gradient descent is the in between. After a certain mini batch, which is like maybe if let's say you have 6 images, a mini batch can be 2. Okay, so if we go back to the previous diagram, like a mini batch over here, like this mini batch is 2, and the top one, the mini batch is 3. Batch size is 3 for each mini batch. Okay, so this is a more efficient way of updating. So in general, the consensus between most deep learning practitioners is that mini batch gradient descent works the best. It converges fast, and it doesn't really require that much passes through of your entire data set. It's very important because modern data sets can be gigabytes or terabytes big. You can spend days looping through one batch. So imagine you do batch gradient descent, you might take years to train your model. Okay, so mini batch gradient descent is a middle ground.
Can I check, does the stochastic gradient descent and the mini batch gradient descent, would it result in it almost the same loss?
Okay, so it really depends on the data set. So ideally, if the function is convex, okay, then stochastic gradient descent would probably get the same result as mini batch because they all head towards the minima. But the stochastic gradient descent might get easily stuck at some like local minima. While mini batch gradient descent, because it averages out the gradient across the batch, right? There's a chance that is able to get out of it. So there's some advantage in mini batch gradient descent in terms of getting to the local minima that can outperform stochastic gradient descent. So I would say it really depends on the kind of data set that you're using and also like the kind of loss function you are doing. So there's many factors that come into play. Yeah, but it is in general nicer to use a batch method to update so that you can avoid like going to some local minima early. Yeah.
Okay, thank you.
Any other questions that you all have? This is an important slide, by the way, because this is saying why modern methods use mini-batch gradient descent. Okay, I mean, of course, if we have big enough computes, okay, maybe next time we have like quantum computers, you know, everyone might use batch gradient descent. Okay, but as of now, mini-batch is still the way to go.
So for the sake of people who might ask why there is a point where the stochastic gradient descent gets stuck, let me try to explain and see whether like my explanation is correct. So in deep learning, there's this thing called early stopping. And why you want to do early stopping is because you don't want to keep training, using up resources to train when the model doesn't get any better after a certain point. And this is a technique because you can train forever without the deep learning model getting any better. So we use this technique called early stopping. So why would you get stuck is because you may enter a value that the stochastic gradient descent reaches and it sees that it's not getting better. However, this is not the global minimum, and there is actually a better, the model can get better. Unfortunately, it is stuck because of this early stopping. So mini-batch gradient descent, if I understand correctly, averages out such that you don't get stuck so easily. Is that right?
Yeah, partially right actually.
Okay.
It's true that you don't get stuck in local minima that easily if you average out, like aggregate stuff. But I don't think it has much to do with early stopping. I mean, sure, you can use early stopping to try to basically prevent your model from overfitting. Okay, but in this case of gradient descent, each of them can overfit. Okay, I mean, each of them will benefit somewhat from early stopping. Again, early stopping, since Chicken brought up this point, okay, maybe I need to draw a diagram here to let you all know. Okay, so early stopping is a method that is used. Okay, let's say I have, yeah, I'm so sorry that I'm drawing this over this diagram. Let me see if I can find a nicer slide to draw it on. Maybe here, yeah. so for early stopping, it's like this. So you have your loss. Okay, maybe your loss matrix. Okay, you have your loss, and then maybe we put epoch over here. So you all know what an epoch is right now, right? An epoch is a pass over the entire training set. Okay, so that's an epoch. So we have an epoch here. Usually our loss for the training loss, we expect it to go here. So this is for training loss. Okay. So train loss usually, because neural networks are very good at fitting a function, they will just keep fitting and fitting and fitting and fitting and fit until basically it does the training set prediction almost perfectly. Okay, but the catch is if it was that easy to train a network, everyone would be done by now. The catch is there's this thing called the test loss. Okay, so the test loss is what you're interested in. Okay, it's typically done like that. So you have a test loss over here. So the test loss is generally what we are interested to find out. Like it can be data that's unseen in the training set. Okay, the fact is that if you train it too much here, this is actually the overfitting realm. So in the overfitting realm on the right, maybe let me just draw the arrow. So this part here is the overfit. Yeah. So of course, the part that is on the left is called the underfit. Okay, so I'm not going to draw that, but this is the overfitting realm. So if you train too much, right, your train loss can go down, but your test loss goes up. Okay, so early stopping is a way to try to counter this by having a thing called the validation set. So the validation set is like you take your training set, you split again into another set. So in this case, you can have your validation set like this. Yeah, actually your validation set should follow sort of like the test set. So the moment your train loss goes down, but your validation loss like doesn't go down, like basically if your validation loss doesn't go down, like you wait for a certain amount of patience, which is like a certain number of epochs. If the validation loss doesn't go down anymore, okay, then we stop the training. So we can use the validation loss as a proxy to test loss, and we can stop here. So if we stop here, then this is called early stopping. Yeah. So what Chikin mentioned just now, early stopping is basically a method, okay, to just use a validation loss in order to predict whether the network overfits or not. Okay, Chikin, this is similar to your understanding. Yep. So this is what this is a technique used in deep learning. I myself actually don't really subscribe to early stopping, okay, because sometimes you might hit this kind of early peaks, okay, and then you might miss out on the potential dip. Yeah, so actually it's not as clear cut as what I drew here. In some data sets, your loss can actually like that go up, then go down again. Yeah, quite a double dip. So sometimes you may not be able to get this part here because you stop early. Yeah. So again, as you learn more about deep learning, there's a lot of things that are there's not really stated what's a clear-cut way to do it, because there are many ways to achieve it. So you just need to get the idea that we are trying to fit this function well, okay, and then there are various techniques that could do it. One way is early stopping, but it need not work all the time as well. Okay, all good. So yeah, back to the slide. Okay, the slide over here, nothing to do with early stopping here. Okay, it's just basically the gradient update will probably not reach local minima that easily if you use batching. Okay, questions? All right, so this is an illustration of the process. So you see stochastic gradient descent, if we were to do our batch updates, because it can be quite noisy, some go up, some go down, it takes quite long for the updates to reach the minima here. Okay, but a batch gradient descent, because it averages out over all this noisiness, it only goes forward. Okay, this is a very nice illustration of batch gradient descent. Okay, but yeah, this is quite ideal also. So mini batch gradient descent averages out some of the noisy fluctuations, and it goes like a little more zigzag, but it still reaches here. Yeah, so of course, if we could do like batch gradient descent, it would like hit the minima more easily, but it just takes too long to do batch gradient descent. So that's the key point. For those who are wondering, these circles, they are actually just contour lines for your loss function. Like maybe this part is the minima, so this one maybe is loss of 1, this loss of 2, loss of 3, loss of 4, loss of 5, and so on. Okay. All right, so before I go on to this slide, I would like to just say that whatever I'm going to cover here is a little more advanced, okay? I just included this here for completeness, so that once you play along with the TensorFlow library, you understand what an optimizer is. Okay, but I don't expect you all to actually know what this is. Okay, because to be honest, this itself can be a 3 hours lesson to talk about optimizers. Okay, but what I want you to take away here is that there are various techniques that we can update our gradients. And I'm just going to share with you some of the broad concepts of these techniques. Okay, if you are interested, there's a very nice blog post, okay, at the bottom here, okay, that talks through some of the math involved as well. So do check it out if you're interested. So what are optimizers? Okay, optimizers are basically ways to adjust your update parameters of your like weights and so on, in order to make sure that like it hits the minima faster. Okay, so momentum. Let's talk about momentum first. Okay, momentum builds on stochastic gradient descent. Okay, you can imagine a ball rolling down a hill. Okay, so this is your ball. As the ball rolls down the hill, it gets faster and faster, right? Because it has the momentum from the previous time, right? So in some sense, if we use momentum, okay, let's say our initial gradients are like that, like that, like that, like that, like that. You realize that actually the up and down portions cancel out, okay? But maybe you realize the trend is that it will go straight, right? So if you use momentum, we try to make it such that the ball will go towards the direction that is like not cancelled out. So you can see that with momentum, your parameter updates get pushed towards what is consistent in the past. Okay, so based on the accumulated previous gradients, okay, if the parts cancel out, okay, then you don't really extend your gradient there. But if the parts complement each other, you push the gradient further in that direction. So the idea is that if let's say you have a loss function, like maybe what you've seen in the previous slide, okay, like what you see in the previous slide, you have a loss function that goes to this point. If you were to use momentum, maybe you will end up something like batch gradient descent. You just go straight to the minima. Okay, but of course, you know about this thing about momentum is that, you know, sometimes if you reach this point here, sometimes if you have a momentum that's too great, you can just like you can, oops, I missed the minimum point, I overshoot, I go to because of all the momentum behind me, I might go to a point that's even beyond the minimum point. Okay, so this may not be a great thing, right? So someone has came up with it, and I think that someone is called Nesterov, okay, because that's the name of the next method. So the Nesterov accelerated gradient method basically says that, okay, I do want to keep track of my momentum as well, but I want to have some eyes to predict what's ahead. So if let's say ahead is like a cliff, okay, like maybe if ahead is something like something like this, a cliff, okay, we want to like not just push ahead like that. We don't want to make the ball just go ahead like that. Okay, we want to take into account that, you know, at the next update, there's a cliff, so maybe we want to go up the cliff instead. So Nesterov accelerated gradient takes into account future positions when predicting future gradients. So they extrapolate what the future gradient would be. Okay, so that's the difference between momentum and NAG. Okay, the last four methods here, okay, are quite interesting. The last four methods here are saying that, okay, you know, for the gradient descent here, okay, let me just clear the entire screen. You know, for gradient descent here, our parameter update over here, this learning rate is the same. This parameter update is the same for all parameters. But what if I want to have a separate factor here, a separate function here that is dependent on my weight itself? So based on the previous weights and like based on the previous parameter values and so on, like, is there a way to make my learning update different for each parameter? So each parameter has a different gradient that we update by. Okay, that's the idea behind adaptive learning rates. So instead of a one-size-fits-all approach to update all my gradients for all my parameters, I make my parameters have different gradients. Okay, that is based on some properties like root mean squared of the previous accumulated gradients. So that's other grad. So people soon realize that this method has a problem, because if we were to do something like this and we accumulate the gradient root mean square, and you actually, this is divided by the root mean square of the gradient update, this part here actually goes big. Okay, this part here goes big. It becomes big. So the gradient update will become smaller and smaller, and then eventually you will not update the gradients at all. So there's a way to counter it. The counter is to do some decaying gradient update, so that we try to minimize this big. So basically, we want to decrease the total accumulated gradient size. Yeah, so this is decaying. So I will not go into details here. Okay, the details, please refer to the blog post that you've seen down there. Okay, other delta. Oh, just for information, RMS prop is by Hinton. Okay, Geoffrey Hinton, if you don't know him. It's an unpublished method that's referred to commonly as lecture 6A slide 29 of Geoffrey Hinton's Coursera online class. Okay, because he proposed that method there, but it wasn't published. but it's quite useful. So RMS prop is one of the, I mean, I find that RMS prop works quite well. Okay, usually. Okay, so I personally, this is my preferred method. Actually, my preferred method is this. Okay, because SGD will work for most cases. Okay, sometimes you use this kind of more complicated methods, it may fail at certain cases. So usually I try this first. Okay, then after that, maybe I'll try one of this. Yeah. So other delta, they also replace this constant term here, this learning rate. We replace this learning rate term by some previous parameter updates as well. Okay, so there are a few changes in this. So Adam is very, very similar to using RMS prop, but then you add this momentum term to keep track of previous gradients. So all these methods are quite well known. Okay, Adam is probably the most well known. Okay, I think maybe Chicken has heard of Adam before. Yeah, or maybe any of you. So Adam is one of the like go-to standards for learning rates. Okay, but my experience with Adam hasn't been very positive, I would say. And I use Adam, it tends not to get the right minima sometimes. Because if we recall what I described earlier with momentum, sometimes you push the ball too much, right? Okay, you may overshoot the minima, and then you may not be able to come back. So there's always some risk in trying. Sure, it converges faster because I keep pushing you towards the direction you are supposed to go. But there may be a case whereby we don't actually hit the right spot because you overshoot it. Okay, so actually there are more and more ways to do it. So there's also NADM. I was thinking whether I should describe it, but yeah, NADM is basically you do a look ahead with Adam. So you put the Nesterov look ahead together with the gradient update for Adam, and you get NADM. Yeah, it's very complicated. It sounds easy, but NADM is super complicated. Okay, so yeah, these are just some of the optimizers that for your information. Yeah, I just pause here for a while in case you all have any clarifications. Okay, again, I would like to emphasize that you don't have to know how all this works. Okay, I just want to give you a feel of what you can do with this kind of gradient updates. Okay, I'll move on. So this is an illustrated view of how like the optimizers work. So like in this case, this is like a saddle point. You can see the different optimizers over here. So over here you can see, wow, adder delta updates very well. Yeah, I mean, you might think that adder delta is the best, right? But actually adder delta doesn't work too well for a lot of other things. Yeah, maybe for this kind, adder grad, RMS prop, NAG, momentum. You can see SGD is probably the only one that gets stuck at this saddle point here. Okay, because it didn't get pushed away from the minima. Because the other one, maybe they have some form of like momentum from earlier on, they get pushed away. Yeah. So this is why like the traditional SGD may not work that well. Okay, but only for certain cases. Okay. So typically my experience is SGD actually updates pretty well. Okay, so yeah, let's move on. So there's this thing called TensorFlow Playground. Yeah, I encourage you all to try it out. Okay, so you can actually like feed in your features, like you want x1 to be like separate x2 is like the horizontal line, x1 is vertical line. You try to classify your like data into like different regions. You add in the hidden layers, and then you can play out the weights of your network will be the thickness of the lines. So yeah, you can change your batch size and training test data. Okay, in the interest of time, I will not be like playing around with it, but the link is here. Do try it out yourself. Okay, they promise that it will not break no matter what you do to it. So do test out their claims. Okay, so far I've been playing with it for a few years already. It hasn't broken yet. So I think it's quite valid. Yeah.
Yeah, this is very good. As in, I've used this before. It's good because then you can understand what each node is doing, and you can try different I can't remember what is it that you try, but on the left.
Maybe I'll just just go through like one instance just to let you all know how to play around with this. So this like is a visualization tool for you to train it. So like your final activation, you can use ReLU, sigmoid 10H, maybe you can use ReLU. So let's classify an easier data set, maybe like this over here. So we do a horizontal line, vertical line, 4 neurons and 4 neurons, hidden layer, 2 neurons, output layer. Let's just no regularization. Okay, I didn't cover L1, L2. Okay, but you can just Google it up. It's just regularization of all this. Do you know? So classification or regression. Remember last week we talked about the two different loss functions that we can use. So classification and regression. So we can see, oh look, a tool, a 4 hidden layer can already classify it. In fact, if we just use 1 neuron, I think we can classify it. So it's just one straight line. We don't even need a hidden layer. We just need one. Yeah. So like stuff like this with 1 neuron, you can't really do much. Maybe I do like 4 neurons. You can see, oh, you see 4 neurons because you can do like a sort of AND function. Remember last week I was talking about AND or OR function. You can do one decision boundary like that, one boundary like that, one boundary like that, one boundary like that. Then you can just like AND the parts together. You can get this region here. So you can do it with without even with just one hidden layer. So yeah. So stuff like this, you
can also change the batch size on the left and the noise. So like why I recommend this is because you can visualize what the model is doing in real time, each epoch that is going through. You can see if you change certain parameters, which you will change in the future, you visualize what the model is doing.
Yeah, so you can change the noise here, and the noise will basically make the data more like noisy. So like over here, if you change the noise, you see the orange and the blue gets more messed up. So when we train it, it still does pretty well. So you can then see like what's the loss, training loss 0.143, the test loss 0.185. So you can see that like over here it fits pretty well because it has learned the right structure to represent the data. Okay, then of course the holy grail is like this spiral data set, which this doesn't work. So yeah, I mean, to make it work, you probably need to add more hidden layers for nodes. Okay, I leave it to you all to play around with it. It is quite fun. Yeah, do spend some time playing with it. You can visualize quite clearly how the decision regions are made, and then like how the weights are updated. Yeah. So yeah, this is how we do this. Okay. So I'm gonna stop my share now. Okay, and hopefully that gave you a flavor of how to use TensorFlow Playground. Okay, back to the slides. Okay, I do have quite a bit of slides to cover, so I will just go through a little faster. Okay, so last week, I think it was Brandon that asked me about like how to do continual learning. Okay, so I'm just gonna just touch on this here as a slide note. So like normal data, let's say you have collect like 4 weeks of data and then you do some prediction, you have to train like in terms of like sliding window. You take the sliding window of the last 4 weeks data as training and then update with the last, you predict for the next week. Okay, but this can be like inefficient in the sense that you need to train for the entire data here. Okay, which is like 4 weeks worth of data. Okay, but if we were to like just train from the previous model point of this data, we just add one more training batch here. Okay, we can actually like continually update our model with the next training batch. So this is called continual learning, and it is a way to like update your model online. Okay, like you collect one batch of data, train it, then you update your model parameters. So yeah, just do take note. There are some things that you can use to help to speed up the online training. You need not necessarily train from all your data from scratch. You can just take the last model checkpoint, last model parameters, and then just train from there. Okay. All right, now for the math. Okay, everyone. Last week, I know someone asked me with regards to, I think it was Takuma, what is the cross entropy loss, right? Remember? So I've decided to expand on it and give you the full math, okay, behind it so that you understand what is cross entropy. Okay, because today we'll be doing fashion MNIST and we will be doing the cross entropy loss. So first up, what is a softmax? Okay, softmax, you can treat it simply as this equation, okay, or I mean to make things simpler, okay, what this is doing is basically converting the output of your neural network, which is like any arbitrary number, okay, to probabilities, solve probabilities. Because what we want to do is we want to make it sum to 1. Okay, I mean, if you look at this equation here, you already can see that it sums to 1 because like you summation over all the possible output logits here. Okay, and then you at the top, you divide. The numerator is just one of these logits. So if we were to take all these sums here, like x, x1, x2, x3, x4, eventually this top sum, okay, will be the same as the bottom sum. If we do a summation of at the top sum will be the bottom sum as well. So this is why softmax gives you like probability sum to 1 because of this way of like mapping your data into like exponential terms. Okay, why softmax? Okay, let's move to the next one. So this is how a work example of softmax is like this. So suppose we have 3 classes, apple, banana, and pear. Okay, these are arbitrary. Okay, of course we can use other classes. Okay, so the output of my network in my last linear layer gives me 3 outputs, like 1.5, 2.5, and 3.5. But that's not good, right? Because we want to get the probability of like the model predicting apple, probability of model predicting banana and pear, and so on. Okay, so we need to find a way to convert these logits into probabilities. So how do we do this? Okay, one way, and the most common way, is to use softmax. Of course, there are other ways. Like you can just take the sum of all these logits and then you just divide each term by the total sum. Okay, but generally this does not give rise to like a kind of peak probability where we want to emphasize one is higher than the other. Yeah, so you can adjust this thing called the temperature. So the temperature is basically a scaling method. So basically you can treat temperature as, before we pass it to the softmax function, we can divide it by the temperature. You divide by a term here to make the probability distribution either smoother or less smooth. So if your t is greater than 1, okay, this will be a smoother distribution like that. Okay, so you can see that like clearly pair is my most predicted, the highest output class. We want it to have the highest probabilities. So my pair is like 0.86 when temperature is 0.5, but my pair is like 0.67 when temperature is 1. But my pair becomes even lower probability when t equals to 2. Okay, but one thing for sure, I mean, even you increase your temperature higher, okay, this pair, okay, will be at least greater or equals to, okay, all of the other class. So the order will be preserved. Okay, in Softmax, the order will be preserved. This one will be greater than this one, greater than this one, and this one will be greater than this one. Okay, it's just the nature of the function. Okay, this is in math terms, they call it ordinal mapping function, which means that it preserves the order of your elements. Okay, so softmax is used, okay, in order to map your arbitrary numbers into sort of probabilities. Yeah, pause here for a while for any clarifications, because softmax is a very important function in neural network classification. It is used almost all the time. Okay, I've never seen a classification that doesn't use softmax actually. Yeah. Most of the time you will use softmax in neural networks.
The activation functions are for just the end node or every node?
Usually for softmax, you will use it at the end of the network. Okay, because you want to predict output classifications, the probability of each classification. But in the middle, if you were to do this, you might lose quite a lot of information because you are artificially restricting your output between 0 to 1. Yeah. Okay. So cross entropy. Okay, I know this is a little heavy. So feel free to tune out this part if you want to, because you don't need to know how to use it. You don't need to know how it works in order to use it. Okay, but of course, I would like you to understand this if possible. So cross entropy basically says that if my predicted distribution over here, Qx, is the same as my true probability distribution, then my cross entropy loss should be 0. But if the predicted distribution differs from your true distribution, then I want my loss to be greater than 0 or a higher value. Okay, why this is the case is because we want basically what you want is you want your predicted value to be your ground truth, right? So this function just helps to accelerate this process or helps to bring that probability there. And just to let you all know, cross entropy may not be the only function that can be used. Okay, there's also other ways to bring the probability distributions towards each other. Like there's a earth mover distribution, which is called the Wasserstein distance. Yeah, you can also use that. Okay, but cross entropy is the most commonly used. Okay, so a work example. Okay, suppose your apple banana pair class, it is supposed to predict pair. So if your model predicts this probability after the softmax layer, 0.2, 0.2, 0.6, okay, we do the cross entropy calculation, we realize that the loss is like 0.74. Okay, but if the model predicts perfectly 0, 0, 1, then you will see that over here, you see 0 times log 0, 0 times log 0, 1 times log 1. Okay, over here log 1 is 0. Okay, because all these are log base 2. Okay, 2 to the power 0 give you 1. Okay, so 0 times log 0. Okay, actually log 0 is negative infinity, but following math convention, this term evaluates to 0. Okay, so this is the loss function. So you can see that in deep learning, we want to minimize our loss. Okay, so by having a cross entropy function like this, we are trying to minimize our loss by making my predicted distribution as close as possible to your true distribution. And that is how classifiers work in deep learning using this loss function. It's pretty cool actually. You can apply any loss function as long as your loss function pushes your model towards making the right predictions. So it is very versatile compared to all the other machine learning algorithms before neural networks or before deep learning. They are like fixed into one kind of structure. But neural networks are like Lego bricks. You can mix and match, you can build different things into a giant pipeline. Just apply the right loss function and you get the right, and hopefully you get the right behavior. So neural networks are very versatile, and cross entropy is just one way to make your target distribution, your predicted distribution, same as your true probability distribution. Yeah, is this understandable? I hope that I have not overwhelmed you all with the math here. Okay, I tried my best to minimize it. but I hope this is clear. Takuma, you asked the question last week. Are you clear now, like how this cross entropy works?
Yes, better understanding.
Okay, that's good. Okay, so if no other questions, I will go now straight into the programming part for today. So, all right, now this will be the lighter part, and I think it will be an easier part for all of you. Okay, I mean, if you know how to read code, this should be a walk in the park. Okay, so fashion MNIST classification. So before we go into the classification, I would like to introduce to you what is fashion MNIST. So fashion MNIST consists of fashion items. So you can see here there are like 10 different classes: t-shirt, trouser, pullover, dress, coat, sandals, shirt, sneaker, bag, and ankle boots. Yeah, so these are some of the, so one icon here is one image. Okay, there are 60,000 training images and 10,000 testing images. Okay, and the image size is 28 by 28 pixels. It's a model size, modest size in like 4 or 5 years ago. Now it's considered small. Okay, because like we have stuff like ImageNet, yeah, hundreds over pixels, you know, thousands of pixels. Yeah, people do video prediction. So why we use Fashion MNIST? It is a small data set. You can train it much faster. Okay, and this only has one color channel. It's grayscale. Okay, other data sets sometimes they have 3 color system. Okay, so this is what we need to know for Fashion MNIST. So I will step you through the TensorFlow code that is needed in order to do this classification. So we have the following methods: load data set, define model, compile, fit, and predict and evaluate the model. So if you all have done the sklearn section, right, you realize that this one is, you know, sklearn, they also have fit, predict. Does this look familiar to you? Okay, so it is actually very, very, very similar to sklearn. Okay, in terms of like how you do this. In fact, I think sklearn has something like evaluate as well. Actually, maybe not, yeah. But fit and predict are actually similar. Fit just fits the model, predict just predicts the output. Okay, so are you excited to go through this? So this will be how to implement deep learning using TensorFlow. I really like TensorFlow because TensorFlow, I think, is the most beginner friendly in terms of implementing a working network from scratch. Okay, so this is how we load the data set. We first load TensorFlow, and then we take the Fashion MNIST data set from TensorFlow. Okay, I will go through this in Colab as well. I'm just going to talk through this so they are aware of what's going on in the notebook later. So we split our data into training images, which is the 28 by 28 pixels, the labels, test images, and the test labels. Labels are 0 to 9 based on the classes in Fashion MNIST you saw earlier. Okay, after that, we can see the shape. So as you can see, for shape, the first one is the number of samples. So in training images, we have 60,000 of them, and each of them is 28 by 28 pixels. Okay, the training labels, okay, there are 60,000 labels as well because one sample corresponds to one label. You need to have the ground truth class. So yeah, the test is 10,000 and 10,000. Clear so far? Okay, so this is the data set. So now we define our model. Okay, so remember in the MLP, okay, we have different model sizes. So in this case, we have a model, okay, that takes into account your input. So your input, let's say this is your input diagram. Okay, so your input has 28 by 28 nodes. Okay, we actually need to flatten it out. So 28 by 28 is 762, I believe. So your input layer is like that. Okay, and then we have a second layer for your MLP, and your second layer consists of how many nodes? Second layer consists of 1 to 8 nodes. So over here you see this thing called dense. Dense is actually known as a fully connected layer, or in other words, a hidden layer. Okay, so finally you have a dense here also. Okay, it may be output layer as well. So this last part here is 10 nodes. Okay, we also do the same thing. We do a fully connected layer, which is a dense layer. We do 10 nodes. And then after that, what we do, we need to basically go through a softmax function. Soft. And after the softmax, you all remember what's the loss we use after softmax? Anyone? After softmax, what's the loss function we use to evaluate our model?
Cross entropy.
Yes, thank you. Cross entropy loss. Yeah, so this is the pipeline for the system. Okay, I realized maybe I should have drawn a slide to illustrate this pipeline. Okay, so this is the pipeline here. You can see that over here when we use like a plot model utils, we can actually see this as well. Input, flatten the layer, then we go through a dense layer of 1 to 8, then we go through a dense layer of 10. Okay, then after that, the loss. So how do we code this out? We can use the sequential API. We go through sequential, and then we go through the layers, like first layer is input, second is flatten, then dense. Okay, you can see that we did not need to use stuff like tf.gradient tape, which was used in the last notebook, because all these are done under the hood within these layers. So if you're interested to do like all this like gradient tape, maybe you only need to use it if you are a researcher like me. If not, actually for commercial applications for known layers or try and tested layers, all these are like Lego blocks. Okay, all these are already defined nicely by other people. You just need to mix and match your Lego blocks and you get your model out. So yeah, I hope this is clear to you. Just remember to put like a square bracket when you put all these sequential layers stacked together. Okay, I see a chat in, okay, documentation of Keras. Okay.
So I'd just like to add that this is the thing that you will be coding the most often. You will see this line of code the most often when you are doing the model, because this is the most basic model that you will build in a deep learning set. I just want to just add a few points lah. In any model, you will have an input layer. You don't actually have to have any middle layers. You can go straight to the output. But the beauty of deep learning is that you, like what Chongmin said, you can build Lego. You can have as many dense layers as you want. You can have different activation functions for each dense layer. You can tweak it how you want. And I think for beginners, it's a bit of trial and error. You can trial the activation functions, any one that you want to try, you see how it works, see whether it works for this one, doesn't work for this one. The reason why there's a flattened layer is because you're using an image data set, which is array. Usually, if it's just already a flat layer, meaning like, let's say bananas, apples, pear, you don't have a grid, you don't have to have this flattened. So there's some things in here that is unique to a image model.
You could also like do some form of reshaping before you fit into the model. Then you don't need the flattened layer already.
The most important thing is your input must be correct. When you clean your data, whether it's an image or whether it's corpus text, or just a simple classification, you need to be very aware what your input is, because your model will give you a lot of errors, a lot of problems, and you won't know what the error is. Most of the time, or a lot of times, is because your input is wrong. And unfortunately, the error, the error codes, not always very clear to tell you that the input is wrong. So you have to be aware. Dense layers are fully connected layers. There's alternative to the dense layer is a dropout layer, meaning you can have some nodes which are not connected, and maybe Chongmin will explain why you want to have some.
Sorry, the alternative is not dropout. Dropout is a regularization method to help it to learn better. But if you want a sparsely connected, you probably have to either change the weights yourself, or you do some masking, which is you mask the weights after the activation. So if you want a sparse network, is currently not easy to create from this off-the-shelf layers. You need to do some custom code.
Right. Okay.
If you're interested in dropout, I can talk about it. I didn't include dropout because I think that is something later on. Maybe you can talk about it next week. Dropout. Yeah.
It's one tool you can have in your toolbox for this. You don't have to explicitly. So the last thing to add is you don't have to explicitly state that it's the last layer for the output. The last layer should be a dense layer. But take note that the important thing about the last layer is that you have to use the correct activation function for the problem you're trying to get. Because if you use in the middle, it's not so important, you can try and error. But for the last one, if you use the wrong one, you won't get what you want.
All right, thanks, Chicken. Yeah, so the last layer, like in this case, we use Softmax because we are doing classification. Then you feed in the probabilities. Sort of, I will call it probabilities in inverted brackets because actually it's not really probability. It's more like mapping into something that looks like a probability. Okay, so that we can use cross entropy loss. But remember, when we want to do like regression problem, can anyone just name me one of the loss functions for regression from last week? Okay, it's called mean something. MSE. What does MSE stand for? Okay, so I just say again, mean squared error. So you can use stuff like that for like different problems like regression. And regression, typically your last activation here, okay, you probably don't want to do anything. Okay, you just put none. Okay, because you just want it to be a linear layer. Yeah. So yeah, stuff like that. Yeah. We will not be covering regression problems in this week, the series of this week's. But if you're interested, just feel free to ask me. Yeah. Because I think for neural networks, they do classification problems the best. Regression is like half-half. Yeah, I would say regression, they tend to like overfit quite badly for neural networks. Yeah, you really need the distribution data to be quite varied in order to not overfit for regression problems. Based on my experience. Yeah. Okay, so yeah, let me just move on. So I'd like to just introduce you here also that there's actually something more advanced, okay? But for the purpose of this few weeks, you actually don't need to use this. So this is the functional API method. So remember you saw earlier in the previous one, you actually have to specify like an array of the different layers, but you can also do it in function form. So the benefit of doing in function form is you put inputs, then you do x equals to this, x equals to this, output equals to this. You specify a model, inputs is this, outputs is this. So if you look at it, it's actually the same. Yeah, it's just that over here, what you can do is, yeah, instead of just taking from inputs here, your this layer X here, you can also take from inputs. Yeah, you don't have to like follow a stack. You don't have to follow a linear flow. You can skip some layers. You can do double-headed outputs and so on. So I just put this here. Okay, just for your awareness. Okay, so in case next time you need to do more complicated models, the functional API is actually one of the more flexible ones. Okay, of course, if you want to do even more custom models, you have to like probably code the whole model class yourself, overload the model class. Okay, but that's beyond the scope of what I want to teach you. Okay, so for the purposes of this beginner series, just take note of sequential models. Functional, you can try it out. Okay, functional also quite easy to code. I feel is about the same. Okay, so these are just a few ways to define a model. Okay, after we define the model, okay, what should we do next? Okay. All right, so I put this slide here just to let you all know how TensorFlow does the models. Okay, so just to let you all know. So output shape here, if you do model.summary, you will see the entire model's output shape. So like flatten, you have 32,784. Oh, it's 784, not 762. 784 is like 28 by 28. So after you flatten, this 32 is your batch size. Okay, I hope you remember what's batch size. Batch size means the number of like samples I pass in through every time I run the network. So the batch size of 32. You might be asking me why do this batch size? Two reasons. One is the batch gradient update, you get smoother gradient updates. The second reason is that if we do this batch size, okay, we can actually do vector operations that can perform calculations on this 32 samples almost as quickly as just one sample. So it is using this parallelization of GPUs in order to perform quicker computation. So that's why we use batch size. Okay, if you are interested in vectorization, you can go and like Google it. Deep learning uses a lot of vectorization to speed up inference timings. That is why we use GPUs. Okay, if not, a CPU would suffice, but GPUs help to do this kind of matrix multiplications using batches or using vectors. Yeah. So this is the output shape. So a quiz here. Okay, so over here, okay, we have the input parameter. We have 784 nodes. Okay, the in-between layer, we have 128 nodes. And the last layer, we have 10 nodes. Okay, so how do we get the number of parameters here? Okay, so I didn't explain this last week, but I thought it was a good way to bring it this week to let you all know how this works. So if we have 728 input, 784 inputs, and we have 128 intermediate layers, okay, the number of connections, okay, is actually 784 times 128. Okay, I mean, how to see this? Let me just draw a very simple model here. Let's say I have one node, two nodes here. This is my input layer. I have one node, two nodes, and three nodes as my like intermediate layer. You can see that for each input node, you connect to three output nodes, right? Three intermediate nodes. So there's three. Then for this node here, I use a different color. For this node here, you connect to how many? You connect to three. So what is the total number of weights I have in the model? It is 3 times 2. So it is output times input. I mean the hidden layer here times the top layer here, the number of nodes. So this is the number of weights. So you can see that this is the number of weights. Okay, why do I have this bias term here? Okay, if you remember from the first lesson, okay, other than these weights here, each of these nodes here have a bias as well. Okay, that biases the inputs. So this bias is independent of your inputs. It's just like an additional term you sum up. So your neural network will give you like Wx plus B, right? Okay, so this bias term, how many bias terms will there be for the intermediate layer of three nodes? 1, 2, 3. So you can see that this is like how a simple thing is calculated. So we bring this to 784 and 128. We get this 784 times 128 plus 128, you get this number of parameters. Same thing for this 128 to 10 is 128 times 10 plus 10, you get 1290. Okay, questions? I realize today is very math intensive, but we cannot avoid all this math. If not, you may not understand fully what's going on. Okay, I hope you can digest it. Okay, try to be as less math as possible, but this math is important. Okay, so this is how our parameters work for just this simple. This actually I would call this a three-layer network. You have your input layer, your intermediate layer, and your output layer. So this network only has one hidden layer. Okay. All right, let's move on. Okay, so we move on to the lighter parts. Okay, so now you should be more familiar with how TensorFlow defines its models. Let's see how we compile the model. So compile the model, what does compile the model mean? Okay, actually compile, there are many parameters that you can refer to on the TensorFlow website. Okay, but for the purposes of what we're gonna use, you just need to know that we just need to specify an optimizer. Here we use Adam. Okay, our loss function, which is like the cross entropy. Okay, and then our metrics, we also add in another metric called accuracy. Also, what do all this mean? Optimizer basically is something that is used to update your gradients. So remember, I have one whole slide on optimizer earlier on. So you can put like your favorite optimizer, Adam, SGD, other delta. You know, you can just choose. It's like, you know, mix and match. You choose what you like, see whether it works. RMS prop. RMS prop is my favorite. Okay, so yeah, Adam's not quite. Yeah. So yeah, but loss here is a sparse categorical cross entropy, which is basically your loss function. You want to evaluate your predictions and your actual outputs, how you want to get your particular loss function to train the network on. Okay, metrics is basically, because TensorFlow only computes like your loss, so you can incorporate other metrics like, for example, accuracy, okay, precision, basically other kind of stuff that you want to compute as well. Okay, that you can put inside here. Okay, now we do the easy part. So this is like sklearn. You do model.fit. So what do you fit in the, what do you specify? Your training inputs, training labels, Okay, if you want to have a validation split, which means you split your training data into a validation portion that is not seen by the model and the training data portion, you can do your validation split. Over here, this is a 10% split. Okay, then after that, we specify the number of epochs. So a quick recap, epoch means you run through the data set once. One epoch means you run through your entire data set once. So 5 epochs means you run through the data set 5 times. Okay, so you can see that Keras has already done the fitting quite well. You can do it like that, like that, like that. Like they already specify like all the epochs and what is my loss, what's my accuracy. So you see, this is your metric that you specified earlier. Then if you do a validation split, they also will calculate the validation loss and the validation accuracy for you as well. Yeah. So you can see that the model is learning, okay, but maybe not as much in the test. Okay, the test lags behind a little bit, but it learns quite well. So that's model.fit. Okay, we move on to the next one. It's called model.predict. So after you have fit your model, you want to predict it. So what we do is we then give the output over a batch of inputs. So you just need to do .predict whatever inputs you have here, like test images. And then over here, it will give you, what do we have here? We have the Softmax function. So you can see that all this sum to 1, because remember our model output, we actually apply a Softmax function at the last 10 nodes. And these are just the values for the last 10 nodes. Then in order to do your prediction, you can just take the maximum of this. Like over here is this one, label number 9, okay, which will tell you your class. So if you want to do like, you can also do evaluate. So evaluate will take in your test inputs and your test outputs, and then it will evaluate based on your loss function, and also as well as any metrics that you specify in the model.compile section. Okay. So this is the overall loop of how it should be done. Import TensorFlow, load your data set. This is the normalization part, okay, which basically makes the model easier to train because you normalize between values of 0 to 1. If not, the pixel values can be up to 255, which may be quite big for the gradient updates. Okay, then we specify a model here with a hidden layer of 1 to 8, output layer of 10, softmax function, compile with optimizer Adam, loss, cross entropy, metrics accuracy, fit the model, and then after that, we test the model, evaluate the model. Questions? Okay, this is like more or less the most important slide because in one single slide, I've showed you the entire training pipeline. We just pause here for maybe half a minute for questions before I just show you a quick 5 minutes of how to run the notebook.
I think let's go to the notebook. We don't have much time.
Okay, sure.
If anybody cannot access the notebook in the second link, let me know.
Okay, so this is the notebook. So basically, I will not cover too much in detail here because I already said most of it in the slides. So what I want you to do is like, if you do have the notebook, in order to run faster, you can go to here, runtime. Okay, can you see my collab, by the way?
Yes.
Yeah, so you can upload the notebook like that, file, upload notebook, and drag the notebook here if it's a IPython notebook. Or if you are using what Chicken provides, you can just open it in your collab. You can go to runtime, change runtime type, and you can select a GPU here. Okay, you're allowed to like have a few hours of GPUs a week. Can't remember the number, but by using GPUs, you can actually run the notebook much faster. Okay, it's like on steroids. Right? If you use CPU, you are like doing it very slowly. So first we import TensorFlow. Shift enter to run the code, or you can click on play button to run the code. So, okay, I think I'm running this already. Cell is already running. For a while, I think they are trying to give me. Okay, why is it not? Ah, yes, it was allocating a GPU to me. So the TensorFlow version is 2. I load my data set. I get my training images and my test images. So it's quite easy because you can load the data from the online repository. Okay, if not, you have to load it from your file. Okay, then this is the training images. Then over here, I did a code that I did over here just to let you all see. Over here, if we change the index here, you can see this is a boot. So like so my index is 1000, and like you can just change it yourself. This is like a trouser. You can see what kind of stuff that the dataset has. These are the training labels and images. You can see that it's a 28 by 28 pixel grid of numbers. Over here, these are like the pixel values. Like over here, let's see the 0 again. So 0 was this boot, you see? So you can see that this pixel value also looks like a boot, right? Can you see? Yeah. So this is like the intensity of each pixel. Yeah, this is the data set. Then the label is 9, which in this case, the label 9 means ankle boot, class ankle boot. So that's how the data set looks like. Okay, we normalize this. So we divide by 255, and then you can see that the output here is all normalized. Okay, then we run the sequential model. Okay, we can then even plot the model out. So one thing about this plot model is that you need to have this input layer. Okay, if not, you cannot plot the model. Okay, so the plot model like that. And you have a model summary. You can see your summary over here, which is what we saw in the slide earlier. Okay, you can read all this on your own. Okay, so we do a compilation, and then we do a fit. So we train for 5 epoch, 1, 2, 3, 4, 5. Okay, so you can see that it's training now. So you can see that Keras, they update you the accuracy and the loss like on the fly. You can see how it works out. You can even download this as a history file by just putting like history equals to this model.fit. Yeah, you can get the parameters as well per epoch. So it's quite cool. Yeah, you can do a lot of things. Play around with it. Okay, you can change this model here, change the layers and stuff. So I do have the notebook here, which is adapted from the Coursera course on TensorFlow. Yeah, I think the notebook is quite well done. So I let you all use it here to just play around with it. So you see, evaluate, we can evaluate. My accuracy is 87% on the test set, which is not bad. It means that he has learned quite well. But can we do better? Okay, so I end it off here. So the exploration exercises, I would like to encourage you all to just try to run it. You know, over here, what will happen if we increase the hidden layer? It will train better, of course. What will happen if we remove the flatten? So if we remove the flatten, we can still train it because TensorFlow automatically flattens for you if the input dimension doesn't match. Okay, output layer, if we change to 6, can we still run? Answer is no. Okay, it will give you an error because you need to have 10 outputs. Okay, okay, I'm surprised. I thought it wouldn't run. Okay, see the loss is nan. Yeah. Okay, so yeah, this is what will happen. What will happen if you add hidden layers? It will be slightly better, but not too much. What will happen if we train for more or less epochs? This one I let you all try out yourself. What happens if we don't normalize it? Doesn't work that well. Okay, what will happen if, like, let's say you want to like stop early, like early stopping, like what Chicken was mentioning, you can add in a early stopping callback. Okay, so these are stuff that you can do to like improve your, I mean, this is more like to explore what is done. You can just basically mix and match your own Lego blocks here. Okay, try it out, see what you can do to solve this fashion MNIST. Okay, if you can get above accuracy of 90%, I would say that you did very well for MLP already. Okay, because what you're gonna see next week, and I just gonna end it here. What you're gonna see next week is we will exceed 90% test accuracy using convolutional neural networks. Okay, so MLPs are not exactly the right way to represent this kind of input. So next week we'll see how to do it better using convolutional neural networks. So yeah, I'll end my session here. I hope you all have a fun time playing around with this notebook. Yeah, feel free to ask me any questions and during the week as well if you face any issues. Okay, if not, yep, that's all from me today.